old, rather unfinished books.
Right.
It's tomato soup, by the way.
Nice, nice. Which tomato soup? Authentic one or Nor one?
Or
Nora.
it's Norse copper soup
Kappa soup. Is that some like powder you put into?
into boiling water. Yeah.
Right.
Okay, so
Anyway, we'll
I will
start.
tell you, I haven't written in a really, really long time.
That's fine. You will be writing quite a bit.
Okay, I'm gonna show you stuff first.
Mm-hmm.
I just want to quickly. Uh,
Put one big ass pulyar suri. Oh
oh, you
wait.
can't see shit, can you? This is a
Negation
little
unary.
nerdy.
Yep.
Okay, no, that's it. I've forgotten the rest. The other two was I know it's and or, but I just don't know the terms for it.
Yeah. Conjunction and disjunction.
Conjunction and disjunction.
Which one is which?
Conjunction is and because it is you're conjuncting things. Disjunction is or, and it is both are binary.
What is logic?
Good question.
Yeah, just need to revise some stuff before we go to the following operators.
Yeah. That's I'm writing stuff down from last class. Who are these people?
I don't know.
I'm showing my face. Hi Hems. Hi antagonist. Hi the vegan biker. We are currently revising last Tuesday's propositional logic class.
Last Tuesday, really? Was it last Tuesday?
Yeah, I think so.
Sounds like, I think it feels like much longer, but okay.
Well, it's last Tuesday because I remember I missed yesterday. Or yesterday. I mean, I didn't miss it. I was there. We technically were just doing something else.
Yeah.
Last Thursday, I said I'll push to Saturday, and Saturday.
You're right.
And yeah. Sunday morning or whatever, doesn't matter. Conjunction and binary. Disjunction. Is it DY or DIS?
DIS.
Disjunction or binary. And is an arrow pointing up.
Yeah.
Or is a point. So and arrow up.
Yeah.
And A. And this or is a V. Logic. What is logic? I'm just looking at who's joining. I don't look. What is logic? Tell no. Repeat again.
Study of what?
Study of arguments.
Yeah.
Oh, that's right, huh?
Yeah.
And what is an argument? An argument is a set of propositions which usually lead to a conclusion.
Yeah, and what are those propositions called?
A proposition. A premise.
Premise, right. So, how do you what's the relation, like what's the bigger set, premises or propositions?
Oh, that's a thing.
Yeah.
Okay, wait, let me recap. So what is the question you asked? Which is a bigger set, proposition or premise, right? Oh yeah, we discussed this. Not all premises are propositions. Sorry, not all propositions are premises, but all premises are propositions.
Yeah.
We discussed this, yeah. Because I can just say the sky is blue. It's a premise.
Yeah.
But it's not necessarily a proposition that leads to an argument. Unless I
Yeah.
say if the sky is blue, then refraction of light is occurring. The sky is blue. Conclusion: the refraction of light is occurring.
Right. नहीं सही बोला. It is yeah. All premises are propositions. Not all propositions are premises.
Fine. You are not fine.
Sky. No. He said if I just utter it, then it's not a.
A proposition. Yeah.
Yeah, it's a proposition. It's not a premise.
Hmm.
It's sky is blue is a premise in the argument. It can be an. It can be some. Uh, yeah, that particular.
Now I'm, now I'm confused. All propositions aren't necessary premises, but all premises are propositions. Correct?
Yeah. I mean, like this actually cuts into like philosophy of logic and stuff like that. Uh, we don't want to go there. We just like want to see. We just like in this series we're just focusing on propositional logic. So, I guess that's yeah. You don't really need to note that down, but it's okay, even if you do.
Yeah, it's a premise only when it's in an argument, as in if there are a set of premises, I'm going to a conclusion.
Right.
Super.
Okay. So I guess yeah. Okay. Let's first revise the truth table for each of them. So what would be the truth table for negation? Can you draw the truth table for negation and show me?
I wrote XY.
Ah, that's fine. Nobody cares. Well, you don't need xy for negation because xy like yeah, negation is a unary operator. Oh, wait, don't do that. It's supposed to be x and negation of x.
Oh, right. Okay, I'm gonna scratch that out because that's become dirty.
Yeah.
I'm so bad at like.
No.
writing
This
stuff.
is fine. Like it's like you just need to take notes so that you can refer quickly.
Yeah.
You don't actually need to go through like Russell Marcus's book in order to get like remember basic stuff. Yeah, that's fine.
Okay, I'm gonna do conjunction now.
Yeah. And conjunction is what? Unary, binary?
It's binary. Negation is the only unary operator.
Yeah.
Not bad. I'm remembering a lot more than what I thought I would remember.
Oh yeah, like it's this stuff is like very intuitive, so you don't actually need to remember it.
Give me some credit.
Huh?
It's either you're a good teacher or I'm a bad student. Sorry, I'm a good student.
It's
Is
both.
it a conjunction or disjunction?
The disjunction is true if both the propositions are true.
Yeah. So conjunction is one only, or it's true only when both the premises are true.
Conjunction is yeah.
And then I have to do disjunction. Yes. Disjunction. Someone got bored. Disappointment.
I mean, I don't care. Like I'm teaching you.
I know.
As long as you don't get bored, I don't care.
Okay. Disjunction, it is true even if one of the premises are true.
Yeah, that's right.
There we go.
Okay.
And
Yeah.
What thing that I solved last time?
Oh, forget that. Forget that.
Okay.
We'll get there. Don't worry about it. We'll get there. I think we like inadvertently we ended up proving one of the De Morgan's laws. So yeah, don't need to worry about that. We'll get there when we get to rules of replacement. I'm actually not sure whether I should teach you rules of replacement first or rules of inference first. I guess like the traditional way is to teach you rules of inference before you teach rules of replacement. But we'll see. We'll see. Let's see. Maybe I might experiment with how it goes while if I teach you rules of replacement first.
Okay.
Anyway.
So you're replacing inference with replacement.
Yes. Anyway, so we have got a few more operators to deal with. So we have got how many? We have done negation, conjunction, disjunction. We have to deal with material implication, material biconditional. Those are the two operators that we will be dealing with today, and these are like kind of like they are kind of the most important ones out there, like in my view. So let's just start with material implication.
Okay.
So yeah, so material implication will be the symbol is just going to be an arrow. It's to like it is from left to right.
Okay.
So it will be P implies Q. So the arrow will go from P towards Q.
What if you're Arabic?
What if you're Arabic? I don't
Right
really.
from there.
Yeah, but
That doesn't matter. Propositional logic is not in Arabic. Sorry, I don't want to
no,
You're
no, no,
recording
no.
this.
Yeah, I want to make a joke, but I don't want that to go on record. I guess you got the joke, but okay.
I don't think I did. I'm not thinking. I'm thinking about my material.
I'll tell you later.
Okay.
Yeah, anyway. Yeah, so basically the material implication is just like in natural language you just express it as if then. So you'll put if, then the first proposition, then like comma, then, and then the second proposition. So here you have two parts, right? You have the P and you have the Q, and then it is conjoined by I shouldn't say conjoined, it's joined by a implication arrow. So you have two asymmetrical parts. You have P and you have Q. Like you can't just flip it around. Like in case of and or, you can actually flip it around and it'll be the same thing. But in case of like implication, you can't actually like flip the positions of P and Q. So the positions of P and Q are actually important when it comes to the implication. So there are actually names for each of the atomic proposition, as in the smaller proposition that make up the bigger proposition. So P implies Q itself is a proposition. It is a statement which can be true or false, right? So
Right.
it is made up of two atomic propositions, P and Q. So there are actually names for each of those atomic propositions. So in case of P implies Q, P is called the antecedent and Q is called the consequent, right? So you have an antecedent and a consequent.
So this is what P implies Q, right?
P implies Q. So if you
So
have
P arrow Q.
P, arrow Q. I mean, like the arrow you're pointing is like kind of like inverted, so
Antecedent and consequent. Right?
antecedent and yeah. So the one on the one that appears first, like towards the left, is the antecedent, and the one that is after the arrow is the consequent. So an implication is true when either the antecedent is false or when the when the antecedent is, wait one sec, an implication is true when when the antecedent is false or the consequent is true. Or you could there is another way of saying this. You could just say an implication is false only when the antecedent is false.
You just said an implication is true. If antecedent is true and consequent is if antecedent is false and consequent is true.
Consequent is true.
So then you next decide. I mean, implication is.
Oh, sorry.
false.
Yeah. No. An implication is false only when the consequent is false
No.
and the antecedent is true. That's the only case where it is false. So you draw a truth table based on this information.
So can antecedent be false and consequence also be false?
Yeah, and the implication will be true.
Okay, so it doesn't matter if the antecedent is false or true. If the consequence is false, then the implication is false.
Yep. No. Actually, it does matter because like you could have the consequent as false, but if if the antecedent is true, the implication will be true.
एक एग्जांपल दे देना अपुता.
Yeah.
I'm confused. Can you repeat that?
Yeah. Like yeah, this is the part like that needs some clarity, right? So yeah, like see, an implication is true when either you can write this as not P or Q.
Sorry?
You can write an implication as not P or Q. Like it's false when either it's only false when the antecedent is true and the consequent is false. That's the only case when it is false. All the other cases it is true.
So this will be the not P and or Q, right?
Not P or Q, not and Q. Not
Or
P.
written written and Q. So not P and Q.
Or Q.
Sorry, or Q. If the consequent is false, then the implication is false. Any other case, the implication is true.
No, it's a combination. The consequent is false and the implication is true. Sorry, the antecedent is true. That is the only case when it is false. In all the other cases, it will be true.
Oh, okay. Got it, yeah.
Yeah. So now draw a truth table such that like it will reflect that.
So PQ, not P or Q, both are false.
No. You've written and.
What's wrong with me? I mean, let's not go down that path. Okay. Not P or Q.
Yeah,
If both are
but
false-
when you're drawing a truth table for implication, it's better to put the P implies Q on top rather than yeah. Although like it's analytically the same thing.
Okay.
Yeah, you can put
I'm
the,
just thinking about it. So
Yeah,
P
yeah,
implies Q. If both are false, it is true.
Mhm.
If antecedent is false and the consequent is true, it is true.
Yep.
If the antecedent is true and the consequent is false, it is false.
Yep.
Apart, the rest is true.
Yep. So it's only false when the antecedent is true and the consequent is false.
Okay.
So that is the only case when the implication is true. Now, this stuff, like implication is actually like people misinterpret. There are ways to misinterpret how the implication actually works. Like sometimes what we do is we think that an implication means that if the antecedent is true, then the consequent like necessarily has to be true, like in all possible worlds. Like that's sort of a modal way of looking at implication.
Could you repeat?
Yeah, so like there are some interpretations of implication where you can interpret it as if P is true, then Q has to be true. Like
Has to be?
true.
Oh, okay.
Like it's sort of like like there is sort of like a necessary thing, like P cannot be false. Like it would be logically impossible for Q to be false. So if P is true and the implication is true. So that is something we call like a strict implication, but that's not what we are talking about here. So that will be like modal logic. So this is like, since we are restricting this to propositional logic, so here we are looking at material implication. So the difference is just that like in one case you're looking at all possible worlds, and in this like you're not really looking at that. Like you're just seeing, like when assessing if a given implication is true, all you're doing is that you're looking at P, checking if it is true, looking at Q, checking if it is true, and then running the truth values by the truth table, and then checking if the implication is true. That's all you're basically doing. Like don't need to confuse things like early on. So like for instance, if you read the book I sent you, they talk about like necessary conditions, sufficient conditions. Don't need to go there. So for now, we'll get there eventually, but for now what we'll do is I'll give you certain sentences now in natural language. You have to tell me like whether it is like P implies Q or whether it is Q implies P, etc. And like the yeah. So
I have to tell you which is the consequent, which is the antecedent.
right, you have to tell me which is the antecedent, which is the consequent. So yeah, we'll do like 3 examples or something like that. So if Sparrow learns PL, then Aputa teaches PL.
But both are true here.
Don't need to worry about whether the implication is true. Just tell me which is the antecedent, which is the consequent.
Oh, okay. If Sparrow learns PL is the antecedent, and the Aputa teaches logic is the consequent.
Right. So you kind of made a small error, which is like you included if in the proposition.
Yeah.
So
I should.
yeah.
Okay.
So the if then part is the operator. It is not the proposition. Yeah. The proposition is Sparrow learns PL, and Aputa teaches PL is another proposition. And then the if then is just joining both of these like in a logical relation. So that is the first one. Now let me think. Aputa trolls X only if X is a sophist.
Okay. Aputa trolls X is the consequent. X is the sophist is the antecedent.
Right. So it's so it's like I just switched around. If instead of using if then, I used another indicator of like implication, which is used in like natural language. So there are like different kinds. So given that implies. So I can ask you like this. Me being thirsty implies that I should drink water.
Okay, so me being thirsty is the antecedent, and I should drink water is the consequent.
Okay, now notice this. Me being thirsty is actually not really a it's not like a it's not a well-formed formula. Like it's not in the right form. So me being thirsty is expressing a proposition. So that proposition that's being expressed, like the content of that proposition is I am thirsty.
Right.
So me being thirsty by itself is not a proposition, but it is expressing like some different kind of it's the content of that proposition is that I am thirsty. So the me being thirsty is not actually like a complete sentence.
Yeah.
So that's
okay. So usually premises you'd want them to make sense on its own.
On their own.
Right.
So if I just walked up to you and I told you me being thirsty, doesn't make as much sense. But if I come and tell you,
I'll probably think you're Yoda or something. Does Yoda speak in propositional language? No, it doesn't matter. Go ahead.
but yeah, like if I come and tell you that I am thirsty, then that actually makes sense. Um, so this is where like you're talking about not just like premises, you're also looking at like propositional content. Like
Right.
the concept of propositional content is if I come and talk to you in German and you don't understand German, that's not like it might be expressing a proposition in German, which you can maybe translate to a language that you understand. But if I come and tell you something like, I should maybe give you an example in a language. Like if I come and tell you, "Mera naam Arvind hai," that's like that's a statement in Hindi. But like, what is the content of that proposition? Like, say someone doesn't understand Hindi, like you understand Hindi, so you get what the what is being conveyed to you. So a proposition comes to your mind, like a statement that can be true comes to your mind, whether it be in Hindi or whether it be in English. But for a non-Hindi speaker, that wouldn't sound like a proposition. So it is not actually something they can comprehend. So it might sound like gibberish, while it actually isn't. It actually conveys some um, proposition. It's just that they don't have access to that proposition because of this language barrier.
Right.
Okay, so that is just the like I just wanted to throw in the concept of propositional content.
So like if I don't understand the language, and so what do I do then? Like, am I supposed to?
Yeah, it needs to be translated to a language that you understand. So if I say "Mera naam Arvind hai," you don't understand. I need to I mean, depending on whether I'm motivated to convey that to you. If I'm not motivated to convey, we can just walk our separate ways. But if I'm motivated to convey it to you, I would translate that in a language that you understand. So
Right.
that would convey the proposition to you. Okay, so I think you've drawn the truth table, right?
Yeah.
Okay. Now you can actually look at the truth table and you can derive when like based on the truth table you can
Yeah.
derive when let's derive the negation of P implies Q. Like what happens if
It'll be P or P disjunction Q.
whoa, 1 sec. So negation of P implies Q will be in a bracket.
Yeah.
And
So P implies Q is in a bracket, and the negation of P implies Q is the material implication. So if I have to put the negation of that, this
no,
will
no,
be 0,
no,
0.
don't no, you need to redraw this. Just redraw this entire table with the third column just being P implies Q.
Okay.
Yeah, there are like too many cancellations. It might be confusing. So just redraw that table with the third column being P implies Q, and then yeah. You'll have to draw a lot of truth tables, like at least in this part.
Yeah, that's okay.
Yeah. So now if you just make another column to that table and you put a negation and then you put the P implies Q inside a bracket, it means you're negating that entire thing.
Yeah.
What will be the truth table for that? Right. So when is not P implies Q true?
Only when the antecedent is true and the consequent is false.
Right. So this is the most important part. That is also when the implication is false.
Yeah.
So whenever I'm saying an implication is false, I just mean that the antecedent is true and the consequent is false. So that is like a rule of replacement called negated conditional. That we'll get there. I
Okay.
guess I'm like simultaneously teaching that, but yeah. So you can basically derive that like when someone says not P implies Q, um, you just know that they mean P and not Q. Not P implies Q. Not
Yeah.
bracket P implies Q means P and not Q.
P and okay. So I'm gonna write it down here. P.
Don't think like just look at the truth table. When where is it? Uh,
Yeah. So
yeah,
this is P and Q.
yeah, and that is the same as this, which is not P implies Q. Try drawing the truth table for P and not Q. So you'll have to do this part like sort of in your head because now you're negating all the Q's.
Yeah.
I mean, you can do it by drawing an additional column too. That's not a problem.
Yeah. So first I'll have to. So P is 0.
Mm-hmm.
One sec.
It's fine if you want to do it like for now. If you want to draw an additional column of not Q and then do P and not Q, that's also fine.
Oh, no, I'm fine with that. I'm just like it's the and.
Yeah, yeah,
P.
yeah, yeah, yeah.
So not Q will be 1 and P is 0. P is 0 and 1 and is 1. The
Both have to
uh
be true.
yeah, both have to be true. So 0 and 1 will be false. 0 and 0 will be false. 1 and 1 will be true, and 1 and 0 will be false.
Yeah.
Yeah. So it's the same as
Yeah.
negation of implies Q.
Yeah. So here again you have proved another logical equivalence, which is just a rule of replacement. You just like whenever you have a negated conditional, you just mean that like it is equivalent to saying that the antecedent is true and the consequent is false. So I think I'm experimenting with teaching rules of replacement along with rules of with just the operations.
Yeah.
Okay. So now we can go to biconditional. Biconditional is just going to be like in natural language, if and only if, when and only when is a necessary and sufficient condition. So those are the kind of motifs you are going to find when you are finding a biconditional. A biconditional is just going to be P Q joined by a double-edged arrow.
Okay.
So instead of having arrow pointing towards the right, you have a two-sided arrow.
It's called just biconditional. It's not biconditional implication or anything like that.
No. It's called a biconditional. Yeah. Conditional means it is an implication. The other name of implication is conditional.
Okay.
So, yeah, you can call it either a material implication or you can call it a conditional. Doesn't matter. Which is why biconditional means two conditionals. Right. So, right. So, a biconditional is. So, when do you think a biconditional will be false?
If any of the premise is false. No, wait. If and only if. Yeah, if
Think of it as a conditional in both directions. Like P implies Q and Q implies P. That is what a biconditional means.
No, okay. P implies Q and Q implies P. Oh, okay. So you asked when a biconditional will be false.
Yeah.
I mean, I'm thinking of it in natural language.
Mm-hmm.
I'm thinking if and only if. So I'm thinking if both ifs are true,
Mm-hmm.
then only then the natural language will be a conclusive proposition, right?
So
Or
it
like
it will be true.
only if both are true.
Only if both are true. What if
In
both are...
not only.
Right. So that part is correct.
Yeah.
A biconditional is true when both have truth, like when both the propositions are true. But what if both the propositions are false?
That'll also be true.
That will also be true. So the only cases where it will be false is when either one of them is false.
Mhm.
So now can you draw the truth table?
Yeah. Are you seeing it?
Oh yeah, 1 second. 0 0 1 1 0 0. Yep, that's right. So why don't you just try proving that too? Like, oh, by the way, let me ask you. Why do you think the case where the antecedent is false and the consequent is true false in this case?
The antecedent is false and the consequent is true. That's false, no?
That's false, but why? Like in case of single directional conditional, like just an implication, that case is true. But in this case, in the biconditional, it is false. Why do you think it is?
I don't know. I don't know why it is false in material implications, but in biconditional, it is satisfying both if conditions. Only then it is true. If it doesn't satisfy either of the if conditions, then it will not go through. It'll be false.
No, but there's an easier way to think of it. If you think of it, think of a biconditional as two conditionals. So I asked you, like, when f is when the antecedent is false and the consequent is true in the single implication case, what will it be? Will it be true or will it be false? Antecedent is false and consequent is true.
It'll be true. True.
It'll be
It'll be
true.
true. Oh no, it'll be false. That's the only case it'll be false. If
No, that's it'll be true.
you said when the antecedent is true and the consequent is false,
No,
right?
no, no. Antecedent is false. Consequent is true.
Okay. It'll only be false when the consequent is false and the antecedent is true.
Yep.
So any other condition will be false. So it's false.
Yeah. So if it is like antecedent false, consequent true, what will be? What will it be?
It'll be true.
The implication.
Yeah, the implication. Sorry, if the antecedent is false and the consequent is true.
An implication will be true.
True. Yeah.
Yeah. So why? So, but in the biconditional case, if the antecedent is false and the consequent is true, it's still false. What do you think is happening there?
Hmm. I don't know the relation between biconditional and material implication. So
The relation is
I
that
think.
it is just like P implies Q and Q implies P.
Okay. Shall I derive it? Maybe then I'll
Yep,
maybe
sure,
get.
sure, sure. Yeah. You'll
So I'll just.
you might, this is a big this thing, so you might need to invert your book, like rotate your book clockwise and draw like
Okay.
uh
I'm
horizontally.
doing P implies Q, and then Q implies P, and then P implies Q, and Q implies P.
Yeah.
So if both are false, it is. One second, I got this. It is false only when the antecedent is true and the consequent is false. Apart from that, it is true in all cases. And in the opposite case, who joined? Others joined. In the opposite case, it is false only when the consequent is false and the antecedent is true. So false here. And then and will be true only when both are true. Everything else will be false. So I derived it. I got it.
One second. Yeah, P, Q, P double implies Q. Yeah, you can call it double implies, by the way. P implies Q, Q implies P. Yeah, you derived it, right? So now, why do you think the like if the antecedent of the by the way, fine, let me just answer your question. Like yeah, biconditionals can have antecedent and consequent. Like if you write P implies Q, P will be the antecedent and Q will be the consequent. But if you flip it, then Q will be the antecedent and P will be the consequent. It just depends on perspective. So it depends on how you write it. If you write it as P double implies Q, then P is the antecedent. In any case, if P is false and Q is true, why do you think the biconditional is false?
If P is false and Q is true, why is the biconditional false? Yeah. Because
Yeah, you're getting there.
P becomes the consequent and Q becomes the antecedent for the second condition.
Yes, exactly. So when you have an antecedent, true antecedent and false consequent, that that implication will be false. So that's why, yeah, the easy way to remember a biconditional is if both truth values are same, it is true. If either of the truth values are different, it will be false. So if it is true, 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 false, false, true, and any other case it will be false. So that's the easiest way to understand a biconditional. They just have to have the same truth value. Both atomic propositions need to have the same truth value. And yeah, so like generally you will see things like yeah, like when you are trying to like define things and stuff like that, you have like you use a biconditional. Although I should mention, definitions by themselves are not propositional. Like if I say the definition of a chair is like a wooden piece of furniture that blah blah blah, that actually is not a proposition. But again, that's like that like it'll be getting into a bit of semantics, I guess. But generally, when you want to express some kind of definitions, you use a biconditional. So something like three-sided shape. A closed three-sided shape double implies a triangle. Get it?
No, I don't.
So if there is a
Okay, so three-sided shape, biconditional triangle will be the is what you're saying
is a biconditional.
Yeah, because if it's not a three-sided shape, then it's not a triangle.
Yeah.
Which means the conclusion is true. And if it's a three-sided triangle and it's called a triangle, then the condition is also true.
Yeah.
But if it says three conditional,
if it's not, so no, think of it this way. If it is a three-sided object, then it is a triangle. If it is a triangle, then it is also a three-sided object. So it goes both ways. So that's why, like if I can just define that as define a triangle as a three-sided object, or I should say a three-sided shape. So if it's a three-sided shape, it automatically implies that it is a triangle. And if it is a triangle, it implies in the other direction that it is a three-sided shape. This might not apply in case of this also applies in case of rectangle. If it is a four-sided shape, it is going to be a rectangle. If it is a rectangle, it's a four-sided shape. Doesn't apply in case of squares, because squares can be, well, yeah, it
Divided
doesn't. Yeah, if it is a square, then it is a four-sided shape. But just because it's a four-sided shape doesn't imply that it is a
yeah,
square, because squares can be. Um, oh, quadrilaterals. I should add. Yeah, quadrilaterals. Yeah, right. Quadrilaterals, not rectangles, because four-sided shape can be a quadrilateral. Rectangle needs to have 90 degrees. I am getting
yeah.
into math. I don't want to get into geometry, but yeah. Anyway, so yeah, so I think for now we are done with kind of all the operators that we use in
Yeah.
propositional logic. So we have the, can you count without looking? No, tell me which ones.
Five. Oh, okay. Negation, consequent, negation, conjunction, disjunction, biconditional, and material implication.
Right. So those are the five operators that we use in propositional logic.
If I'm not wrong, antecedent and consequent is also a concept in music. It's called call and response.
Oh, yeah. Yep, that's also a
So,
concept in music. That's right.
for example, sa re ga ma pa would be, what am I singing? Sa re ga ma pa will be the consequent, and then pa ma ga re sa will be the like consequent.
Oh, right.
Usually, like, musically, you're asking a question, and then so it's more like it's going to the dominant. Dominant is usually the fifth
Right,
in a
and
scale.
then you're resolving back to
Yeah,
the one chord.
yeah. You can resolve coming to one, or you can resolve in the sixth, or you can resolve in the third also.
Right,
Usually
right,
depends if one chord, right? So
right.
sixth would be oh my god, I forgot. Oh my god. It doesn't matter. I don't want to. I haven't read music in a long time. I forgot what it's called.
That's fine.
It's
That's
called
fine.
the first consequence false. It doesn't matter. We're learning proposition only. It's not music.
That's fine.
I'm gonna go revise my music later.
Yeah. Anyway, so I'll give you one example, and you tell me which is the antecedent. Let's just. Oh, by the way, how is a biconditional like used in natural language? A biconditional is used with like if and only if. If you see a motif like that, I I will buy this product if and only if my salary comes through. So
Yeah.
it's like, yeah, so it will be like if and only if.
Or it can be like only if I get my salary, I'll buy that.
Oh, that can be an implication, not necessarily a biconditional.
Only if I buy my get my wait, why? Only if I get my salary, I'll buy that.
Only if I get my salary, I'll buy that. That is like, you can, it can be confusing, because an implication can also be um mentioned that way. Because see, ultimately a biconditional is like a is like a category, is like a type of implication only. It's
Yeah.
just conjunction of two implications. So
Mhm.
you like, people might get confused whether you're talking about like a unidirectional implication or like a biconditional.
But I'm saying only if, right? Which means that the if conditions should be satisfied.
And that's true in the implication case also.
Mhm.
So that's why if and only if. If and only if means both have to be true,
Okay.
right? So that's why it's like,
We get that. I think when we start using natural language examples, are probably like understand more, I guess.
right. Yeah. So yeah. So I can maybe give you like a few more examples, right?
Yeah.
I organize my PL classes when I am free.
That will be a material implication.
Right. So what, like, if I want to translate it formally, what will the translation be?
What is the natural language name again?
I will organize my PL classes only when I am free.
If I am free, then I will organize my
Yeah.
proposition logic.
Yeah, that's right. So let's look at some more. Uh, I will teach you propositional logic on the condition that you use it in daily life.
If you use it in daily life, then I'll teach you proposition logic.
Right. Um, yeah, so that, but yeah, one second, one second. Let me give you another example where this is like. Hmm. Let me see. There actually isn't like good examples for this. I have to make something up. Oh, this is going to be a. This might be a little bit hard, but I'll give it to you anyway. So
Doesn't
me
matter.
me defending carnism is sufficient to say that I am a bad person.
If I defend carnism,
Mm-hmm.
then I'm a bad person.
Right. Yeah. So I guess you're getting the implication. Like, you're getting a drift for like how to translate natural language to implicate like yeah formal language.
Yeah.
Um, yeah, and it's like it's just like in case of biconditional, it's just going to be if and only if. That's like when and only. Okay, you could be like, I will go to the lake when and only when you go to the lake.
Yeah.
So that will be like a biconditional. And if like I will go boating if and only if you go boating. So it means like both propositions have to be true. Okay, okay. So we have gone through all the you know
Operators.
all the operators. Now I guess we can what should we do now? I don't know. I'm just like I don't have a plan, so I'm just probably going to um, wait 1 second. Okay. Uh, yeah, just draw a truth table for P and not Q. Give me a sec. I'll be. Yeah, I'm back. No, no, no. P and like conjunction.
Oh, okay. Okay. Natural language disaster right here. Okay, I'll do it. Wait, so P and not Q.
P and not Q, right?
Okay, okay.
Okay. 0 0 0 0 1 0 1 0. A. Why is 1 0 1? Why?
Why
Why?
is Oh, because this is Q, not Q. So
Right.
PQ,
Exactly.
not Q will be one. So one will be one.
Right. Correct. Correct. Okay. Yeah. Now draw a truth table for P and not P.
Okay. Again, it's P and not P, not
P and
P.
not P. P conjunction,
There
not
we go.
not P.
The other little anxious part is I'm putting my intelligence out for everyone to see. You're saying not many people see your channel,
Huh?
huh?
Yeah, that's
You're saying
that's
not
one
many people.
thing.
Wait, sorry. P and not P. I don't know why I did Q. I'm gonna scratch that out.
Yeah. And we'll do one more truth table and we'll call it a day for today and resume on Tuesday.
Wait, intuitively, I'm telling you, P and not P will never be one.
Right.
Intuitive.
Yeah, you're right.
Okay. Because whenever when it's zero and it'll be one, 1 0. So it'll never, both the conditions will never be true.
Yeah, exactly. P not P. Okay, 0 0 0. Right. So you can mark this as the truth table for a contradiction. So this is why when you derive a contradiction from a given um, any proposition, if you derive a contradiction from that, you can simply reject that proposition, like because it goes all the way back. Like everything is false. Like think of it as the proposition as the antecedent and the contradiction as the consequent. You have F in the consequent, so it goes all the way back.
Okay, I'll probably take some time to understand what you just said.
Yeah. We'll get there. You'll get there
Yeah.
when you understand when we go through rules of inference.
Okay.
But yeah, this is a truth table for a contradiction. Now, draw me a truth table for P or not P. So instead of and, you just have a disjunction.
Right.
P or not P.
Oh, this will be all will be true.
Yeah.
Yeah. There we go.
Oh
Your
wait,
camera is gone.
camera is yeah. Yeah, now it's fine. Yeah, P or not P. Yeah. So this is why a P or not P is called a tautology. It's always true.
Tautology.
Yeah. So we have like contradictions, which are always false, at least in classical logic, and you have tautologies, which are always true. So yeah, I guess that's enough for today. Um, Next time we'll start with taking some more like a little bit more complicated propositions, and
Okay.
then drawing truth tables for them. So that'll be fun. We'll have like multiple operators.
Putting my intelligence for public display.
Anyway, yeah, I guess that's pretty much it for this one. So I'll just end the recording.
Before you end the recording, let's show this to people.
Kings
Kings ditch
ditch
wings.
wings. Oh,
Deep.
deep shit, deep shit.
Let people know
Deep.
that kings ditch wings.
Deep.
Yes.
Yeah, it's coming. It's
Oh,
ironic
let's
coming
let's
from you.
let's actually do that with prop logic.
Actually, no, wings
If
doesn't mean
kings
that
ditch
for me.
wings,
Huh?
sorry. If you ditch wings, then you're a king. So it's not a bidirectional. It is the other one.
It might help, but if you like uh if you cut out the grammar stuff first when constructing something in PL, it kind of helps. After that you can put in the grammar.
Right.
Like in for that you could have done if wings then king, and then you could have gone into if you are etc etc, because it just lesser words means you can organize your thoughts better.
Yeah, yeah.
Yeah.
If wings, then king. So it's a material implication.
If ditch wings, then kings. It
If negation of wings, then kings.
If
uh
if if wings
Sparrow.
equal to if wings equal to not king, not uh, not wings equal to king.
Spa-
Yes,
Sparrow's face deep in thought looks like a
majestic.
kid. Yeah, exactly. Like a kid ruler kind of thing.
by the way, Sparrow, it can be a bi-directional too. Like if you're
Yeah,
a
that's
king,
how
yeah, if you're a king, then you will ditch wings. If you ditch wings, then you're a king.
You are a
you're
true king.
king.
Only you are a true king if only you ditch
Only
wings.
Yeah.
Yes,
Right, right.
Only if.
only if it
If
is.
and only if.
Uh, if wings, then negation of king.
Maybe we can we can remake this
separate
T-shirt
column.
with remake this T-shirt with like kings and then like a bi-directional and ditch wings.
Hmm.
The recording is down. No.
No, no, no. I am ending it right now.